I suppose we should start our official meeting. Today, we were sort of intending to follow on with a discussion from 2 weeks ago. In the latter part of the presentation 2 weeks ago, Jesus was presenting some ideas from the interaction theory, but from the point of view of relativity. And in fact, he just started to introduce some of the notions that I sort of hope to focus on today. But also, I like to connect to what Dr. Subchik was talking about in terms of the duality that is important aspect of the algebra that is related to relativity very directly. And this was, of course, a favorite theme of Ushevich for a long time. And most of the ideas that I'm focusing on now were summarized around 2017 in a document that I think I should have it here. Yes. Yeah, okay. So I'll get to that in a minute, I guess. So is everything working properly here? I'm not sure. I seem to have a different layout in my screens today than I had in the past. That's what I get for upgrading Zoom, perhaps. Things change a little bit. Yeah, there we go. Okay, that's more familiar. Yes, so of course, I don't feel as organized as I would like to be. So if you bear with me for a moment, I will get this presentation. This is so I'm going to show some slides that are part of a larger presentation, but I want to focus on just one part of it. So let's start with this.
Okay, now we can see the
Okay, great.
presentation.
The main point of these slides, actually, as I mentioned, was to present or to summarize the main contents of this paper by Ushevich. This was published in a short form in 2014, but this was one of a number of papers that Ushevich and I worked on together. In some, my contributions were very small, usually just a matter of asking questions, and so those questions resulted in revisions over a period of about 3 years or so. So that the copy that I have here was last revised in 2017, but it was a kind of ongoing process. So this is the sort of the main reference that I want to mention here, and its main goal of this paper was actually to present the concept of center of mass in relativity, but relativity as expressed in this groupoid form that Oshevich preferred, where the velocities were binary velocities. They're well defined between two objects, unlike conventional relativity, which Oshevich showed the concept of velocity actually always required a separate observer, or sometimes he referred to this as sort of the ether, and he viewed that as a flaw in conventional relativity, since it led to many problems. One of the problems was specifically the problem of definition of center of mass, which has been a long-standing technical problem in relativity. And so this paper presents the concept of center of mass from that point of view. Let me see if I can go through here. But in order to get there, he presents a very succinct summary of relativity, and it's really that I wanted to present in this these slides. I won't get into the notion of center of mass or dynamics, but it's actually in the dynamics that follow from the definition of center of mass that connects with the subject that Jesus was talking about, that is interaction theory, where we consider bodies interacting with each other. And of course, center of mass requires this notion of interaction to consider bound states between bodies. So in any case, I want to, as I said, I wanted to focus not so much on relativity per se, but on the mathematical formalism, since that's what connects most directly with Dr. Sobczyk's presentation. So we won't focus on any of this. Instead, we'll jump directly to the algebraic part. I think you just mentioned some of these issues, these concepts before, but the general idea is that we want to start very abstractly and axiomatically, in that we don't begin with the notion of vector space at all, but instead just an algebra, and then define linear operators, linear differential operators on this algebra. These operators are what play the part of the vector fields in conventional development. But the definition is dependent only on Leibniz. Like the only axiomatic assumption here is that these linear operators obey the Leibniz rule, and all of the calculations are done in a coordinate-free manner, but they require this Leibniz rule as to become effectively part of the algebra.
How about the dimension? Is dimension? I come up with AI. There's no limits on the sum.
There's no concept or no requirement that we define anything like dimension. Dimension is a matter of representation, as is that. So we haven't assumed any basis here, and we aren't actually using coordinates here, but I wanted to give that the coordinate expression as an example of what's meant by linear differential operator.
Of course, that's like the gradient operator, thinking about AI as a vector.
X, thinking of X as a vector. AI is a scalar coefficient, right? In that expansion in terms of some basis. But the vector itself is just this linear operator X.
But of course,
So-
A is in algebra, so it could be a matrix algebra or any other algebra, I suppose.
Yes, A is a most generally an R algebra, that is some algebra built on top of a ring. But that ring could be any ring whatsoever. Generally speaking, however, in physics, we consider algebras over fields. And so, but most of this development doesn't require the notion of a field here at all.
May I ask if the algebra can be non-associative or
No,
restricted?
it's definitely associative.
So Lie algebra is close in the definition of A.
The Lie algebra enters in terms of the algebra associated with the derivations,
Yes, yes.
Right.
Of course,
not with respect to the R algebra that underlies it. Right?
again, universal enveloping associative algebra over Lie algebra. Lie algebra is the attached antisymmetric algebra of the algebra A. Yes, yes, indeed.
But an essential notion here is the notion of a co-derivation, which again is a linear operator that maps derivations into the algebra. And together, these derivations and co-derivations form a vector space and its dual. But we don't need very much of that, right? We don't. Shevich was quite keen on the idea that linear algebra is introduced too early in the curricula, right? That he was quite fond of the idea that one should not separate calculus and linear algebra, and rather that linear algebra sort of is a consequence of introducing the Leibniz rule into algebra. So when we add this Leibniz rule, we effectively make the algebra non-associative, because these operators X, right, are not associative in general, and that's what gives rise to the Lie algebra
Yes.
of derivations. Right? And there is a corresponding Lie algebra of co-derivations or differential forms. But in fact, the Lie algebra structure is not all that important here, because we want to go directly to Grassmann algebra or exterior algebra built on top of the derivations and co-derivations.
Could you say a little more about how the Grassmann algebra arises? Or that's using the exterior product, I guess.
Exactly. Yes. So this is nothing unusual here at all, but the important point here is that in Oshevich's development, this is where the nilpotent structure arises. That we are going to consider Grassmann algebra in terms of creation and evaluation operators. So the creation just being the left part of the exterior product, right? But it is nilpotent. I didn't write. You can see that it's nilpotent from this expression, for example, right? Which
Excuse me, Professor Pech. I have here a question about the name derivation and co-derivation. Because I try to understand those, like going in the category in opposite directions. But here I understand that you are using referring to derivation vectors and covectors. I think that it's in that sense that you are using that, but this is my question.
Well, this I'm using only the notion of derivation here as in the sense of well, directly with reference to this Leibniz rule, right? So that a derivation is just abstractly a linear operator on the algebra that obeys this rule. I don't require the same thing of a co-derivation. The co-derivation is a linear operator that maps derivations into the algebra. But I don't. Are you suggesting that there's a Leibniz rule associated with co-derivations? Is that? Jesus, your microphone is off.
Yes, yes. And yes, I understand that, but in fact, we can introduce a Leibniz rule here with forms, and then this part of
sorry, with what? I didn't understand you. Introduce the Leibniz rule.
Here inside of the forms, the scalar forms.
It completely analogous to expression number one.
Because in it's something more
Sorry, I'm having trouble with your audio. It seems to be interrupted.
The form.
No, it's not clear to me what you're saying, that because this operator X, this linear differential operator X, is operating on the algebra A, right? And we express the Leibniz rule in terms of an expression in the algebra A. But the co-derivations operate on derivations, not on elements of the algebra, but rather on the derivations themselves. Right? So it's, so if, so I don't have a way to say evaluate a co-derivation over an element of the algebra.
Okay. Okay, thanks. I think I understand. Thanks.
Like we, let me see if I can do this. So if I were, how can I do this here? Can I do some annotation maybe? So, so in particular, we don't have a way of say writing say alpha of small x, right? Come on, we don't have that, right?
Okay, yes, because it is acting on the operator x.
Yes, yes, we have this.
Okay.
Sorry. Just struggle with trying to draw here properly.
Okay. Okay, that's.
Okay, let's move this around. All right. Try again. All right. So the nilpotent operators that we define here are called creation and evaluation. This is terminology that was Wojciech used in his most recent sort of publications. Of course, these operators have a long history. I mean, creation is just the exterior product, and evaluation is referred to as inner product or inner derivative, but Wojciech didn't really like this terminology, and in particular, he developed a series of class notes that were used during courses at FESC, and I think there's one reference that I'd like to point to directly here. Are the class notes that he used for courses on electromagnetism, and I have a copy of that here, and I think it's unfortunately still only available in Spanish. Let me just find it here. Okay. So this is a fairly large document. It's effectively a textbook, and it goes through all of the subjects that I'm talking about here, but in a much more pedantic way, like intended for sort of upper level university level course in electromagnetism, done entirely in the formalism that that I'm just starting to introduce. And he gives all of the sort of historical background. And this was actually part of a project that Shevich had over quite a long time of presenting calculus completely without the notion of coordinates, like developing calculus completely axiomatically, but in a way that could be used directly at beginning university level courses, and perhaps even earlier. I mean, he at some time he presented the idea that these ideas should really be discussed at the level of high school algebra or high school level calculus. But this book, these class notes at the current time, I think would be very valuable to eventually have in English. It would be to make it more widely accessible. And I did discuss with Shevich over a number of years, but about the possibility of doing exactly that. But unfortunately, we just did not have enough time to commit to something like that. But I hope that this does happen at some point in the future. Jesus, I do have a question about these class notes. Has the university decided sort of what they would do with materials like this that Dr. Shevich was, this Vigna was using in his classes at UNAM?
No, I don't know, but I think that there is not any decision about this. I know that all of them are there in academia, in Google Academia. Then I remember that there are about 100 different publications there.
Yes.
But institutionally, there is not nothing about.
Yeah, it's a question for me, like how to contribute somehow to continue this idea of making these fundamental ideas available to a wider audience, and without Professor Savage there to bring this forward.
Can you give more examples of actual simple calculations that a student would do? Or where do the calculations arise? So far, we haven't come to any calculations to see how it works or ties together.
Well, let me skip back to so it's differential calculus over rings and the relationship to classical calculus. This one. Yeah, so
found intriguing is that when the formulation is brought to such a level of abstraction, of total coordinate free, then realization makes no sense. In other words, because basically the totally abstract formulation, it includes all conceivable possible practical realization. And therefore, an isotopy, for instance, the isotopy of this I don't think will make much sense to me because because there is no need. It is included in the formulation itself. That's what I'm saying.
Yes, I agree. And this is sort of one of the discussions that we had early on, I think, when you were, Dr. Santilli, when you were presenting the idea of isopity, I had some difficulty distinguishing how one would discuss the isopity without introducing a representation. So, and the concept here is that all of this development is representation free, that all of the calculations are performed abstractly at the level of the algebra extended with these operators, like without any reference to coordinates at all, right? Even with, and as Dr. Sobchak said at the beginning, I mean, or this question implied, right? We don't even talk about the notion of dimension at all. And as you'll see in a minute, we also don't talk about space-time in the same way, right? Although we still have a notion of what something being time-like and space-like might mean, but these are presented entirely in an algebraic way.
I agree fully because the isotopy appears, it is a physical instruments for doing practical models. And by conception, the isotopy of an algebra coincide identical even with conventional realization. What is the case of the algebra? When you go to the abstract level, by definition, you should see no difference. All differences appear when you go to the coordinate-free level. Yes, I agree fully. Yeah. Isotopy emerged only in physical application. This is not the case for the reversibility. No, that's a different, totally different angle. As far as the isotopy, yes, I agree, Paul, and it is nice for me to see it because it's also an illustration of the power of mathematics. That, when you reach a certain abstraction, you include, such an incredible variety of relativisms. If I remember well, when a long email I wrote to Dr. Cruz regarding his axiom for interaction, and this was, I consider, excited me a lot because it was so abstract to include, it's therefore so powerful to include a long list of physically, not mathematically, of physically different realization.
Okay, well, let's skip out of this and go back to where I was. Just a minute. Maybe just to summarize, the point that I was trying to make was that Ushevich considered this algebra and this abstract approach to be the only tool that was needed, so that we should in principle be able to take someone from high school and who's familiar with the notion of algebra and immediately introduce the notion of the derivation, just by insisting that there is this additional axiom, Leibniz rule. The difficulty is that this presents some technical difficulties in the algebra itself for solution, but it doesn't prevent the solution. So because the Leibniz rule introduces a kind of non-associativity into the algebra, right? And so solving systems of equations in the algebra extended with this rule results in algebraic system that is more challenging, to produce specific results, like to calculate, say, how should I say, the, what's the right word to do, how to say this? I mean, ultimately, we need to look at values like this AI here, values in the underlying field, and in order to make measurements. But the important point here is that we don't have to introduce a specific representation. We don't need a specific basis. We're going to describe, for example, material bodies just in terms of a derivation alone, and possibly also a co-derivation. But we're going to do all of the calculations in abstract form, without. But we still need to actually come up with a number that describes, say, the relative velocity, the magnitude of the relative velocity between two material bodies. But we would do that without introducing a specific frame of reference. Okay, where are we going here? So again, I wanted to contrast the way that the nilpotency enters here is different than the way the nilpotency was presented by Dr. Sobchak in his construction of Clifford algebra based on dual Grassmann algebras.
Dr. Page, I have something to say. So I have difficulty in understanding nilpotency at this abstract level. Can you please elaborate in a little bit more Austrian language?
And so it's a nilpotent operator in the sense that if we were to, say, operate using creation twice, the result is 0, right? So it's like,
now I get it. Yes, of course.
Right? I mean, but these are operators, right? So if we were to say creation of X operating on creation of X, right? Then this is the same as writing creation of X exterior product X, right?
Very nice.
I should have written this out a little more explicitly, but
you explained it very, very clearly.
okay, and it turns out that evaluation inner product is also very easily abstractly defined in terms of the pullback of the creation operator, and it also is nilpotent in that sense, right? That if we operate twice by evaluation, or if we apply the same inner product twice to say a 2 form, then again the result is 0. Right? But we want to represent the algebra in this form because we're going to consider combinations of creation and evaluation. Jesus last 2 weeks ago used the word creation and annihilation. This is also reasonable terminology.
Yes, I do that because I reserve the term evaluation for the case in where vector are of the same degree. And then I was using only in that case evaluation.
evaluation.
But yes,
The way in which, say, we would say that a co-vector evaluates a vector, is that right?
in this way.
Yes, but that of course is included in this definition of evaluation here.
Yes. I agree. Totally.
Okay, so the next interesting level discussion is the idempotent operators, because that follows the same pattern that Dr. Shobjik presented, but the algebra here is very different and somewhat more abstract. So from these creation and evaluation, or creation and annihilation operators, we can construct two idempotent operators. That is the combination of evaluation and creation in alternate orders. Oops, I'm sorry.
Yeah, that looks very familiar, actually. It's just another way of getting at the same structure, it looks like to me.
Well, maybe. Like
Yeah.
that's
Yeah,
I'm not-
evaluation basically reduces down the dimension, whereas creation raises the exterior product then.
yes, here we would say it increases or decreases the degree, right?
Okay.
And- sorry. So here, for example, for some reason I can't.
Okay.
A minute here. I'm sorry, I'm just having a bit of trouble navigating. If I can do that. Yeah. So you see here, this is just a notation saying that we're increasing the degree of the form or multi-vector, right? And evaluation is decreasing the degree.
Okay, that's clear.
Okay, but what else should I say about this? One sort of significant thing here is that these two operators applied, like the evaluation creation applied in different orders, produces can be thought of as two different tensors in the general abstract sense of tensor. And it's only one of these tensors that you see in tensor algebra. But here, when you've separated these notions of evaluation and creation as separate nilpotent operators, their combination produces two different tensors that have this peculiar property of producing what is referred to here as the product structure. So they
in that number 11, do you ever take the sum of these idempotents? Like, that was important. Oh, okay, there you have it. N plus D is equal to the identity. So that looks, okay, that's interesting.
yes.
Yeah, it looks very similar, actually.
But in fact, Jesus wrote this in one of his last slides, but he wrote that right, he just wrote it in a different order. He said that, you know, if we said that identity minus pi is equal to D, right?
Yeah.
But looking at it this way is useful, because the thing that we want to do is define this notion of split, but in a minute, but let's do this first. So I wanted to point out that this pi operation is a algebra map. That is that under the image of pi, so if we consider all expressions in the overall Grassmann algebra, under the image of pi, we have another Grassmann algebra. And this Grassmann algebra, it in some sense has a how should we say, it has a space-like character, right?
Yeah,
Whereas-
yeah, in Clifford algebra, we call such a mapping like 13 an outer morphism. That's just a different terminology, basically the same structure though.
Well, this would be something like the mapping that you were talking about, Garrett, between, say, space-time algebra and space. Right. So between the
Okay.
geometric algebra of say 1, 3 and the geometric algebra of 3, that's determined by an observer, right, in effect, right? So,
Yeah.
so what Ashevich is going to do with this is that he's going to say, well, that this represents the physical space of an observer.
Okay.
And it's determined by this algebra map that is parameterized by a form, alpha in this case. Right? But the observer is actually represented by a vector or a derivation in this. It's trying to stick to the same terminology here.
Excuse me, but here observer, I am trying to understand like the splitting of the space.
Yes, let's
Ah,
let me go to the next slide.
well,
But before I do that, I also want to point out that the D mapping is an algebra derivation. That is that if we operate with D alpha on the Grassmann algebra, we don't get a Grassmann algebra. we get instead this derivation. So it's an algebra derivation. And we have the same Leibniz rule appearing again, but at the level of the algebra.
Can the derivation represent an observer in motion, or the idea that the representation is for all observer, whether it is at rest or in motion?
Well, at this level, we aren't really talking about physics at all anymore.
Okay, sorry for
Right?
it.
I mean, at this level, this is entirely abstract algebra.
Yes, yes.
But we're going to apply this, like, eventually to the notion of the relative velocity between two observers. Right?
Yes, that was I was aiming at. Yes.
Yeah. So we'll get to that. Right. So we also are going to need a couple of other notions. So I just sort of threw these in here. So the exterior derivative is also defined here as part of this algebra. We can say, I suppose it's at this point it's what the way that Cartan extended the algebra in this form. But we also have things here quite easily defined, like the Lie bracket and so forth. So this isn't that important at this level yet. And here also at this point, we can also describe what we mean by geometry. That is that geometry is built on top of this algebra when we introduce a metric tensor as an isomorphism between the derivation part and the co-derivation part of the algebra. So it's, but this is, for example, how in a sense, how the geometry enters into relativity, because we're going to want to use this mapping that I referred to above here, this pi mapping that maps from space-time into the space of a physical observer, but it's defined in terms of the differential form, whereas the observer is represented by a vector. So the geometry allows us to map from the observer vector into the differential form that we're going to use to perform the splitting, to split out the physical space. Okay, so what else? This is a bit more geometry, but the point here, I guess, is that all of these geometric ideas have coordinate-free expressions in this algebra. Yeah, we can define the notion of connection and torsion, and so we can do all of differential geometry in this abstract, intrinsic way. So, yes, so okay. So, I want to go from here. I wanted to be able to define abstractly the notion of an observer without making reference to any underlying geometry. So in that case, we have the material body represented by a time-like vector. We have a corresponding differential form that obeys this axiom, and that differential form is how we define the clock of the observer, in effect, right? It's how we measure the progression of time. Maybe that isn't particularly clear, but the main point here is that if we're prepared to assume some geometry, then we can define it this way, in terms of the isometry from the metric. And it does have this property that it will evaluate in this form. But in general, we would like to do as much as possible without introducing any metric. And I'd like to present the notion of velocity without the notion of introducing metric.
Excuse me, but in this definition of clock, you are considering that x prime, excuse me, I need a clock for a process x is any co-derivation x prime.
Yes.
So is that x equal 1. But after you are mixing the time from one observer with the process in the other observer.
Mhm.
This is the relation to 20.
Yes.
Then, but it's a problem because for me, excuse me, there is a problem because I don't understand how the information from one observer go to the other observer. Because for this projection, it is necessary that this information are the same for both observers.
You mean operationally, what does this mean if I say that I evaluate the material body Y by the clock of the material body?
Yes,
Yeah.
X.
You're saying operationally, how does observer X accomplish this type of measurement?
Yes, yes. Because X observer can have their own clock X prime,
Yes.
but not have the space of Y.
You mean the well, but this is why
Because
this is the we assume though that the material body Y as a process is accessible within the physical space of the observer X.
yes, but
So
yes,
X is so Y is in the physical space of X and X is in the physical space of Y, and that is required here, right?
yeah.
But at this level we haven't said anything operationally about how to implement this expression 20 in sort of physical terms.
Yeah, I like to just make a comment on 20. I would write 20 in my way of looking at it as x prime times y plus y times x prime is equal to 1. I would say that is what a clock, that's what I was talking about, compatible nilpotents. But it looks very similar to that expression number 20 there, except, oh, okay, so that's right. So you're saying x prime y minus y prime x is equal, oh, is equal, okay. So x prime times x equals to 1, that's a clock. And this, in one observer system, and then y times y prime equal to 1 is a clock in another system. Well, that's
Yes.
anyway, that's very interesting.
So the primes, the x prime and y prime are are clocks, but in two different states of motion, in effect. Right? They are measurement systems for time, but they belong to two different observers.
Oh, okay, that's interesting.
So in other words, if you use your own clock to measure the progression of time, nothing is strange about this, right? Like in other words, X using its own clock, measuring its own progression in time.
Yeah, that's like being on a line in space-time. Time advances. So saying in X prime X equal to 1 is you're on a world line of an observer, it looks like.
Yes. So it's like that considers X to be the proper time, and X prime is how you're measuring that proper time. And so that like, so the classic example in relativity is a twin paradox, right? That the twins measure their own rate of, the rate at which time progresses for them is unchanged.
Yeah, so you're on a world line. That's what it looks like. And different world lines, of course, are in Minkowski space-time.
But this is to say that if someone is in a different state of motion than someone else, then when they use their clock to measure the motion of another body, then they will see time for that other body as progressing in a way that would violate this assumption, right? But 20 is a restriction, is a physical assumption here, or is necessary for relativity, because it's saying that this time will be symmetrical in that sense, right? That if, however X measures Y progression, Y measuring X progression will in time.
Okay, that's a constraint then of consistency of time, I suppose, in space-time.
Yes.
Yes. It's one of the most important hypothesis that Professor Osiewicz was making for his idea of relativity. Because here we are assuming that both observer and in some kind of external reference system that are that make to both observer capability of interchange information. I think that this is the meaning of question 20. And here is one, yeah, go ahead.
I was looking forward to your presentation, Jesus, about interaction, sort of to look at this sort of hypothesis from a deeper level, like, and so as you started to present last week, you assumed that this interaction involves, say, the exchange of a light signal, a signal at the speed of light.
Yes. 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 And then the speed of light, like a constant of the nature, is the background behind this hypothesis.
Mhm.
Okay, maybe equation number 21, you have g of capital X, the metric valued at the event X, and then g of little x. Is g the same metric isomorphism in that?
No,
in both cases?
let's not say event X, right? This is,
Oh, okay,
this is,
event X, okay.
yeah, but this is not an event, right? This is the material process X, represented by a time-like vector, right?
Okay,
So G of the time-like vector is a form, a one form.
Okay.
That's
Yeah,
is that
go ahead, finish. I thought you had finished. I'm sorry.
no? It's okay. I just was going to clarify, maybe try to clarify that we're looking at the metric from this point of view, right? That when we apply G to a vector, we get a form. So this is looking at G as a say a 2 tensor, right? So that when we apply the 2 tensor to the vector, then we get a covector. So we map from vectors into covectors.
My question was still on regards to the equation 20, because it's very intriguing. There are aspects that are intriguing. Could you please, another page, give us a little bit more info on, you hinted a little bit at the way time, the notion of time can be introduced in this abstract formalism, which is, I find it's a very intriguing question. Could you elaborate a little bit? And after that, I have a comment.
Okay, well, time in this formalism is represented by a vector, by and this vector is a linear differential operator. So in effect, time is simply represented by x in this case, right? But we have the notion of time separately from how we measure time, so that we abstractly we have this process or material process X, and this material process X has an associated clock. And this clock is how we measure its progression in time. So in a sense, we're talking about all we're talking about here is time, right? Everything that is shown here is about time, has nothing to do with space at this level.
That's what I have a comment, Dr. Page. In my view, the notion of, that's Dirac, again, the master, one of my master, in my view, and I could be wrong, so please, if you disagree, I will say thank you. In my view, an abstract definition of the notion of time necessarily requires its complement, namely it's the opposite time, because the motion forward in time requires also, in nature we know it exists, motion backward in time. Now, so point number one, and I don't see the definition of the complementary notion of backward in time if you represent time with x, but it's not enough. In my view, the abstract, the introduction at the abstract level, but again, this is the point in which I could be wrong, Dr. Page, so I apologize if that's the case. So in my view, the introduction of the abstract notion of time essentially requires an ordering, because once you, if you represent time with an ordering rather than with a vector, then automatically you have the opposite ordering, and therefore you can represent the motion backward in time. Specifically in the equation 20, and here is the problem. Just a moment. Let me see the equation with my enlarging glasses. So you see is x dash and then we're acting on y. But in my if the action of x dash acting on y is equal to the right, is equal to y acting to the x dash to the left, then an ordering can be introduced in the product. Namely, the ordering of the product can could represent time, in the sense that all multiplication of x dash to the right against y, that represents motion forward in time, and y multiplied by x dash to the left could represent motion backward in time. So in this way, from the same abstract equation, you include both direction of time. Does it make sense? If it doesn't, please say so.
Well,
in my viewpoint, I think that in the splitting of the product x prime x equal 1, there is the definition of time, because here there is a splitting of the space in two parts. One of them is related with a process that is at the same related to the concept of time, and the other is the process of the rule of make the measurement of time that is in the space. Then I think that there is not a problem with this definition here, because this in fact takes like process the motion, and then taking this like process, one can make the splitting in this way. But when we introduce two different observers, X and Y, and recombine the information, I think that there's a strong,
Well, I agree that, because I agree with you, the formulation is so abstract that definitely
I think it is necessary.
that's the power of the incredible power of this formalism is its abstract brought to the ultimate abstraction, which means including lots of things. So definitely you can include the time. So definitely there is no inconsistency regarding time. No, that was not my point. No.
Well, so this, I think what Jesus was just saying is that when we define what we mean by a clock, we are effectively introducing a notion of direction in time, at least for that one observer, like with respect to that process. So we're saying that when the process X measures time, it does so in this way that satisfies this equation, right? So in that sense, time always goes forward for that observer. Time never goes backwards for it. So you don't ever get younger, right? But that doesn't necessarily mean that when one observer measures another body, we haven't said here that means that that this value is always positive. Like so x prime on y is possibly less than 0. So in that case, it means there may be some observer x that when it looks at y, it measures the time for y as being backwards in time. Time gets smaller for y as time progresses for x.
Still from
But so the point is that the direction of time is a relative thing, right? It's not something inherent, intrinsic in a single body, but it could be the relationship between two bodies.
fully agreement. There is no point. My point was a different one. My point is that an abstract formulation should include both direction of times, and and then perhaps I can be but also by operations, such as, for instance, the ordering of a certain operation can if you assume that an ordering of the operation multiply the multiplication to the right, they can represent the motion forward in time. Automatically, you have in your abstract formulation, you automatically have the motion backward in time given by the action of the entity on the right multiplying the object on the left. So through an ordering, you automatically have both direction of time. Again, I agree with everything you said. My only point was a formal point to see whether this beautiful abstract formulation can indeed include both direction of time, because that will be.
Why not just set x prime x equal to -1 for the opposite direction of time?
I'm sorry, could you repeat, please?
Yeah, why not just in equation 20 set x prime x equal to -1? That would indicate measuring time backwards in time.
But
Yes.
the equation for the motion backward in time. While if you assume the product as it is now, it's beautiful because you have x dash y, in which the ordering, the point is all in order. The ordering is undefined, and that's beautiful because it has to be because it is abstract. The theory has to be brought to the extreme of abstraction. But however, the question persists. Then let's look at how this operation x dash y is realized, and then you see two ways of realizing with an ordering to the right and an ordering to the left.
Yeah, why not just set x times x prime equal to -1? So have x prime and x, the clock and the event, be anti-commutative with respect to each other. Then you have.
Well, but remember the algebra here. I mean, these are derivations and co-derivations. And by definition, a co-derivation is an operator on a derivation. So this co-derivation x prime is operating on derivation y. And I don't see at least in this formalism, the possibility of introducing the ordering of operation as having some kind of physical
Why not
meaning.
just define what's meant by an anti-co-derivative or something like that, where x prime times x is equal to -1. You can call it a co-vector as well. It doesn't have to be 1. It could be -1 or some other number.
Well, see, no,
My point
I don't. No, the point isn't in the sort of symbolism here. We're talking really more about metaphysics, right? So we're saying that if we have a single body, a person, for example, then what would this person do in order to consider that they are going backwards in time? I mean, this is like the time travel movie or science fiction book, right? That when you're H.G. Wells and you're traveling backwards in time, you personally are still getting older, right? Right. So your x prime x is still positive, right? But if you're observing someone else, so that someone else is observer y, right? Then if you observe them and you measure what you think is time for them, then this product x prime y could potentially be less than 0. Right? And this would imply that you see y as if they are getting younger, right?
Yes,
But
yes.
right? But it's a relative statement, right? So y is never getting younger from their own perspective. Right? From the
That depends on
If the observer is looking at the clock itself, then that might be negative then, x
well,
x prime equal to -1. That's the observer looking at the clock.
but see, the clock is literally a clock, right? So H.G. Wells takes the clock out of his pocket and he looks at how time is progressing. And as far as he's concerned, like he's still getting older, right? But when you hold that clock up and you look at something outside this time traveling device, then they look at the outside as if it's getting younger. Right?
Well, that depends on the theory. I mean, so
Yeah.
that's not clear. The two direction of the results of the operation on the two direction of time have to be different. This is why my point, not to repeat, but because the action of the derivation y on the left to the co-derivation x dash is different, numerically different than the action of x dash to the multiplied by the derivation y to the right. And this is necessary to distinguish between the physical events occurring in a time evolution forward as compared to a time evolution backward. Still, I honestly, I have some uneasiness in seeing at the abstract level. Again, the abstract formulation also represents all possibilities. That's the beauty of the abstraction. And again, the abstract formulation of time should represent both direction and with the different numerical results in the derivation, of course, and so on. If the results are the same, then there is no actual differentiation between as occurring in nature between motion forward in time and backward in time. But I beg you, those are my own comments. So whatever.
Well, yeah, I mean, I understand sort of your motivation, but I'm still trying to see this in the context of relativity, and I in this formalism, we don't have like so we shouldn't think of this as multiplication. Maybe that's a problem, right? Like these are operators, right?
Those are operators, those are action. I agree fully. Yes.
Yeah. So there is no composition of y with x prime.
No. But I discussed the
because the result of applying x prime to something is an element of the algebra. So
yes.
So when we
I think that in the paragraph you say this because it says the pair x prime is called an observer. It is assumed that the clocks are any two observers, x prime and y prime, and are symmetrical. This last is the enunciations of 20 equation. You mean that time are symmetrical. here there are not problem about the design of the product x prime y, because I think that in this expression there are the affirmation that the relative velocity is approaching or going far for both observers. I think that this is the affirmation in this equation. And then there is here not problem with the sign of time, but with the meaning of relative velocity, that those are reciprocal here. I think that this is the essence of this expression here.
Incidentally, I discussed with Professor Odjevich, the realization of special relativity. I believe there is I have no objection. Dr. Page, if I remember well, I foresee no inconsistency in the formulation of relativity. The problem I'm addressing is a different one. What is the image of the formulation that you derive when treated with time moving backward? And that is, this question depends on how.
But of course, you have to answer the question, what does it mean that time moves backwards?
Means that you get younger. Means that the velocity moves backward, etc., etc., etc. Very, very clear physical. It moves that that's Dirac. It means that all characters anti-hermeticity means that each and every quantity of the formulation of relativity you formulate must have an anti-Hermitian image, which, however, but there's only one way. There are other ways in which you can keep an objective. This is a physical answer, but from an abstract viewpoint, there are other ways in which you can achieve the same results. However, everything has to be opposite. Each and every single aspect, not only the elements, but the operations. The operation, and yes. And the sum of the two realization has to be iso-self-dual, namely has to be invariant under anti-hermeticity, because it is an intrinsic symmetry of the matter-antimatter world.
Well, I like your answer, though. I like your answer, but I want to point out something very specific, and it's sort of something that I skipped over at the beginning, and that is what we mean by a material body, like abstractly at least. So Shevich wanted a material body to be a process, and he used the word process, for example, in the same context as in thermodynamics. So we have a natural direction of time that is inherent in thermodynamics. So given by entropy, basically, right? So that we don't have processes in thermodynamics that allow bodies that are cold to suddenly get hot, right? Right. So that a hot body will over time must equilibrate, right? So in other words, there are no physical processes that allow you to get younger, in effect, right? That there is no such material body which is a material body getting younger. So.
Yeah, but you can't measure an event in the past. So if event in the past occurs at an earlier time, then it's negative with respect to the observer.
Yeah, but that's right. It's relative, right? It's relative to the observer. So it doesn't mean that like an observer can be related to to a material body in such a way that that observer measures the time for that body as if it's progressing backwards in time.
Why can't we say that the clock, that it takes two observers in the same reference frame to agree on what the time is? So say the clock is just the second observer in the same reference frame. And then if it's not in the same reference frame, then it's not equal to 1. So yeah, I don't understand why you need to say the clock is different than the observer. The clock is a second observer in the same reference frame. You can make that identification. I think it makes sense. So it takes two observers in the same reference frame to agree what time is to begin with.
Well, now you're getting close, I think, to what Eustace was talking about in terms of the interaction theory, right? So what we mean by a clock, could be a pair of processes. So you have so a clock is a process, and a human being is a process, right? And so this human being might make measurements using this clock, but they have to interact in some way, right? So this what I'm presenting here is more abstract, that somehow I'm not saying how this clock is operationally implemented. You're suggesting that we have some process like a clock, a pendulum, and we're counting, pendulum swinging back and forth, and as we count this we call this a process, and then as long as this process is in some relationship to the material body, which is using this clock process as a measurement device, then I think operationally we can accomplish what you're saying, right?
Yeah, I almost think that a clock should just be an observer in the same reference frame as the observer he's measuring. So I wouldn't distinguish between a clock and an observer. I would say that a clock is just a second observer in the same reference frame.
But if we put two observers in the same reference frame, this means that there are a third observer observing these two observers.
Yeah, that's a good point. Yeah, don't go so quickly to speaking about reference frames, right? Because right, because here we just have material bodies, right? And the material body is represented as a process. This process is mathematically represented by a vector. That's all we're talking about, right? We haven't said anything about reference frames as such. The closest thing we came to talking about reference frames is when I was talking about these algebra maps, right? That allow you to get from space-time into space from the point of view of a particular observer.
Okay, well, it's interesting whether a clock can be considered just a second observer. And if it's in the same, if they're measuring time the same way, then that means they're in the same system, the same inertial system. So it's almost a tautology, it seems like to me. A clock is in the same frame as the observer. Or you can say the clock is a second observer. It doesn't make much difference, really, what you say, I don't think.
Well, abstractly, you say that the clock is dual to the observer, to the process, to the material process. So it's the clock is the covector that measures the vector, right? So when we apply the covector to the vector, we get the scalar quantity that says, it's what we mean by a measurement. Right?
Yeah, well, that's the interesting thing. And if you look at the polyalgebra as the even subalgebra of an observer, it's really putting the two together. And that's what's missing. If you just consider covectors and vectors, covector mapping vectors into scalars, that's observer dependent. But if you, so I think that the idea of a covector is too restrictive. And that's this idea of compatible inertial, compatible nilpotents, as I defined in my talk. But I don't see that there's so much difference. It's interesting. I think this is the point that's very confusing, that kept me from and Zbyszek from understanding each other for many years, actually.
Well, here I agree that the notion of nilpotent and idempotent is very different. Like, to start with, you're talking about elements in the algebra, whereas I'm talking about operators. So I'm saying, so like, I know in geometric algebra the distinction.
What is the polyalgebra? That's operators. Are they not? Polyalgebra X, a sigma 1, sigma 2, sigma 3 are operators. They're considered as operators, but they're also considered as, well, you can consider them as being vectors in a reference frame.
Well, here vectors has a very specific meaning. It means a derivation over an algebra.
Okay, well, that's different.
Right. So we haven't started with the notion of vector. We started with the notion of algebra, and then we applied Leibniz, and then we said, okay, well, we have these abstract thing called operators that obey Leibniz, but it turns out that they form a vector space. And this vector space has a dual consisting of covectors. And when we apply a covector to a vector, we get the scalar quantity, right? And it's, we don't even have a notion of scalar product or dot product, right? But we do have the notion of evaluation. So we can say, if somebody gives me a metric that is an isomorphism that allows me to go from a vector to a covector, then we can use that covector to evaluate some other vector. And that's what we mean by scalar product. So scalar product and metric are synonyms in Olszewicz's sense of the word. Right?
Yeah, but you can take the covector of a covector, and that becomes a vector again. It's isomorphic to the vector.
No, you cannot take a covector of a covector.
Why not? It's a vector space as well, so it has a covector associated with it, or a double would be the covector.
But it's element from a different algebra, right? There are two different Grassmann algebras. The Grassmann algebra of differential forms and the Grassmann algebra of multivectors.
No, I think it is a theorem in mathematics that the dual of the dual is isomorphic to the original space that you started with.
Yes, that's definition.
Using the metric tensor. Then if you use the metric tensor, then you can go from the vector to covector. But then you need the metric.
Okay. That's right. It's observer dependent, then I guess you would say.
Yes, observer dependent.
So I can say do a scalar product over differential forms if I have a metric that's invertible, right? So I can map the differential form using the inverse of the metric into a vector, and then you apply the second vector or differential form to that vector. That makes sense, right? Geometrically.
Are you going to talk about that third observer type thing we were talking about? I don't know if we're going to get to that today, but that was the original point we were trying to understand, actually.
I think that deserves a separate presentation, right? That is that's a presentation specifically on the how to view conventional relativity.
the idea of groupoids gives to us the opportunity of distinguish the zeros, the 0 points of zero objects of each category. Then I think that this is the problem in relativity, that we need the idea of groupoid, and then in this way we can think about one third observer that are describing to other two, the others two.
That's interesting.
Well, yeah, but it's a separate, definitely a separate subject, because here the notion is only, well, I haven't even discussed velocity yet, but let's just skip ahead here. Okay. Okay. So go back here. So now we're going to use this notion of split to show how to define relative velocity, right? So this expression here is identity mapping, right? So we have remember that these two mappings, pi and d, are idempotents, and the sum of those two idempotents is the identity. So the first equality follows just from the fact that that's an identity. But then we can evaluate that in the following way, right? Where we've defined this relative velocity as in these terms, right? Sorry. So this is taking the process y from into the space of observer x. So this is, in fact, what we mean by relative velocity is when an observer x sees an object y, they see it as in their space, and what we consider as the relative velocity is the same as the process y, the process associated, and process means vector. The vector associated with the material body y is being viewed as in the physical space of material body x. And so when we do that, then result is an expression that is the space-like velocity relative to material body x. But we've made use of the properties of these idempotents to define relative velocity in this abstract way. But the important point is that it involves the material body y and the clock of observer x. And in fact, it's easy to show that if we evaluate this space-like vector, the relative velocity, then we see that it's orthogonal to the clock, right? So that so that in other words, it's the same thing as actually it's in the kernel, right? So that it means that there that this other material body is being viewed in some sense as being simultaneous, right? So that we know where material body Y is now with respect to our sense of what of X's sense of what now means, right? And so we're describing its motion with a sense of the relative time, right? Time relative to the observer. I wanted to include this definition here, not so much to define relative velocity, but rather to illustrate how the mathematical formalism is used, right? So that if I just skip back to yes, to this result here, right? That this product structure pi and d are form something that we can use to split. So we can split. So we can split using pi. We can split out of space-time the space-like part. So that's what we're doing down here, is that in this definition of velocity, we're using pi to split out the space-like part of y.
Okay, yeah. So basically 23 explains 22, I suppose, right?
Yes, if we substitute 23 into 22, then that, how should I say it? That's solving 22. 23 solves 22 for this term.
Mhm.
The thing that's significant here is that this does not involve three bodies, as you said. Like this is just a relationship between two bodies. And time is inherent in this notion of process, right? So that when we talk about x and y, we mean the process x and the process y. But when we talk about observers, we're assuming that there is a process plus a clock, right? And the clock is how we measure the process. So when one observer measures another process, the way I was illustrating above, it does so using its clock. But with the help of this operator pi, right, we are effectively saying that we understand sort of what we mean by the physical space of an object. Right? But that physical space of the object is defined in terms of its clock. So it's like getting the co-basis of a space, so that from a vector that represents a process, we get a covector that represents the clock of that process, and then associated with the clock is the corresponding space-like parts, right? So we're if I said that properly. I mean, I think so. I mean, so that vectors like v here, v sub x, y, those are vectors in the physical space of observer x. Well, I think obviously I jumped into this too quickly, maybe, because you're not asking questions about it, right?
Oh, it's interesting. I think that it can be translated into the way I look at things too.
Well, let me ask it, like, let's go back just to the technical question. If you're looking at this from the point of view of Clifford algebra, this product structure, I would very much like to understand what the analogy would be in geometric algebra to this notion of a product structure. Like, when
Well,
can
that's the
we
thing.
have
You have mutually annihilating idempotents, which sum to the identity one. And of
Well,
course, there you only have two, pi and d, the derivation and the pi. The pi, I guess, works like a determinant, really, on evaluated vectors. It has the same structure.
Well, the first thing is, like, so in geometric algebra, you're going to have an algebra in which things are multiplied. So we're not. So first of all, we need something analogous to the notion of operator. So I was going to say that.
Of course, an operator is like a matrix, a polymatrix, for example.
Well, if we say x and say x and y in geometric algebra, we mean that x and y are multiplied together, right? Using some multiplication in the algebra.
So, a matrix algebra, for example.
You mean assume some representation of x and some representation of y.
Yeah, a linear operator on a vector space. Well, that's what the polymatrices really are, linear operators operating on a column vector, usually the way people look at it.
but you introduced the idea of idempotent elements of a geometric algebra, right?
Yeah, that's right. Yeah, as a Grassmann algebra and the Grassmann algebra dual being what I call compatible, and that's the only structure I need to do everything in linear algebra. So instead of multiplying matrices, we multiply, well, compatible Grassmann algebras. But that's, yeah, then of course the creativity is anti-commutative, and the evaluation, of course, is the same as your vector, a covector evaluating a vector, or a vector evaluated by a covector. So it's just a way of putting it together a little differently, that's all.
Well, so we have these types of elements in geometric algebra.
Well, a nilpotent, of course, is x squared is equal to 0.
Yes, but I'm talking about idempotence here. Right?
Okay.
So
Now
let's,
that's the interesting thing. You can write any idempotent as a product of two nilpotents, what I call compatible nilpotents, and that's exactly like a covector, really.
That's possible in 2 dimensions, however. Are we
Well,
sure?
it's possible in any number of dimensions. That's the interesting thing. Any matrix can be written as a product of nilpotents.
Yes. Let's see, yeah.
okay, well, I'm just trying to express what I was trying to say here.
Okay.
So in geometric algebra, if we have two idempotent elements of the geometric algebra, what do we mean by their sum is the identity, right?
Well, I usually think about the identity matrix as one, okay, canonically speaking, but that's not, well, that's the thing. If you look at isogeometric algebras, then we come to the ideas that Dr. Santilli uses very powerfully.
But well, that's kind of part of the problem, right? Because when this one here that I wrote, x plus y equals 1, is not the scalar value 1, right?
Not necessarily, not at the abstract level, no.
So what element in Clifford in geometric algebra operates like the identity, right? See that, like I can't.
Well, that was my equation. BA plus AB is equal to 1, where
Yes.
A and B are nilpotents.
But
Yes, but here pi and d are idempotents.
Yeah, X and Y are idempotents, right?
Yes.
Yeah, well, yeah, so BA corresponds to the matrix 1, 0, 0, 0. You know, where you have just one along the diagonal and the other diagonal is 0. That's an idempotent.
But is that an element of the geometric algebra?
Yeah. In fact, I consider the matrix 1, 0, 0, 0 to be an idempotent, namely the product of the two nilpotents, B and A. And then AB is the other diagonal element at the bottom, 0, 0, 0, 1. And then I build up the whole matrix. Any matrix then can be represented in terms of these compatible Grassmann algebra structure, where you really have the covectors and vectors built in. And I say that's really necessary when you identify an observer with a Dirac vector which has square plus 1. And that's the split of the Dirac algebra into the Pauli algebra by a gamma 0, which is a world. You can think about the unit vector along the world line of the observer. And, you know, it's very nice. That really is due to Heston. split. So you, at the Minkowski level, that's the level of the Dirac algebra. A gamma 0 corresponds to an observer. Each observer corresponds to a different, well, observers moving with respect to each other corresponds to cosh of the angle between their respective Dirac time-like vectors, gamma 0 prime. Two observers. The dot product, gamma 0 prime is the cosh, is the 1 over the square root of 1 minus b squared over c squared. Yeah, it's just a different way of looking at it. But I think we could just translate directly.
But in your
All the
expression,
equations you have really can be translated.
Put only anti-conmuted the products xy. It's anti-conmutative, and then you get the solution of this system.
Yeah, that's right. Anti-commutativity is
Eh,
built into the structure of the matrix algebra.
yes, yes.
So how can we write x squared equals x?
Well, that corresponds to a matrix 1, 0, 0, 0, you know.
No, but x can't be an element of, well,
It also depends on what you define by the square. The square is a product. The product has a number of realizations, different.
Yeah. Well, here the only assumption I'm making is that it's a Clifford algebra. It's multiplication in Clifford algebra.
For algebra, you have isoclifton, so you can have an isoproduct, isosquare, but you can assume with no problem at all. You assume a conventional product, so the unit is a conventional unit matrix, and everything is standard. And
See, I object to going to discussing matrices because then we're talking about a representation. But if I talk about x and y as just abstract elements of the
Clifford
algebra, or geometric algebra, then as a minimum here, the product of x or x with itself means that x can't be a vector, right?
Well, no, it could be a unit vector. A unit vector squared, a Euclidean unit vector squared is equal to +1. And you can think about the x, y, z axis being corresponding to 3 orthogonal Euclidean vectors. Sigma 1, sigma 2, sigma 3. In an inertial system, you can call those, identify them with the Pauli matrices.
But in Clifford algebra, in geometric algebra, a vector times a vector can't be a vector.
Well, it could be 0. If it's a nilpotent, it's 0. Like if you take E0, E1 plus what I call F1 are anti-commutative.
Yeah.
If F1 squared is equal to -1 and E1 squared is equal to +1, then E1 squared is 1 and F1 squared is -1. If you take the sum and assume they're anti-commutative, then you get a nilpotent. E1 plus F1 squared is equal to 0 because they anti-commute. One has square plus, the other is square minus. So, you get 0 then. So in Clifford algebra, you can have idempotents square equal to themselves, which are not 1. Okay, 1 in the real number system, the only idempotents is 1, other than 0 is 1. Okay, that's the real number system. But if you look at quaternions, then you have what? Quaternions which have square -1, but you also have you can also construct 1 plus the quaternion I times 1 minus I gives you 0 then. So you have nilpotents which are not just 0. In the real numbers, the only nilpotent is 0. zero elements. So you're giving up the
But
feedback.
still, the problem I have is comes much earlier than that, right? So if X is a vector and I multiply it by X, I'll get a scalar plus a bivector, right?
Well, yeah, if you multiply two vectors, in general, you can write it as a symmetric part, which is a scalar, and an anti-symmetric part, which is a bivector.
But we never get, X times X equals X if X is a vector.
But of course, with matrix algebra, you can consider the elements.
Yeah, that's true. In matrix algebra,
You
yes.
can consider
but
them to be vectors in a vector space. But, it's just what you, well, like the Lie algebras, you're considering vectors too. Whatever you call a vector is really, you can call anything a vector if you want to. In fact, what is an algebra? You can call the elements of an algebra vectors if you want to. Well, the dimensions.
What I meant by vector in this context of geometric algebra was a degree 0 element, a degree 1 element.
Degree 1, yeah.
Yes. So if I have something that's in geometric algebra as superscript 1, if I have an element of that subset of the geometric algebra, then we multiply by another element of that same subset. The result won't be in that subset anymore.
Oh, that's right. Well, when you pick out a basis, that's generally a Clifford algebra is generated by P vectors which have square plus 1 and Q vectors which have square minus 1, which are all anti-commutative. So that's the generators of the Clifford algebra, PQ, P comma Q. But you can easily identify matrix structures in there. Well, any Clifford algebra is isomorphic to a corresponding matrix algebra, many different isomorphisms of Clifford algebra in the structure of matrices. For example, the Pauli matrices or quaternions can be represented as matrices as well. But people think about quaternions as being generated by three vectors which have square minus 1 and anti-commutative that generates the quaternions. Ij and k. I times j times k is equal to -1. Then that was Hamilton's great invention, of course. But that's the even subalgebra of the Clifford algebra G3.
Well, maybe my problem goes back further, like, and it's sort of what you have often said, Jared, about like, do we need covectors, right? Do we need co-derivations?
Well, that's right. That's the whole.
That's the
problem.
Yes, I agree. And so I do not know, so I understand like that the derivations could be like a degree 1 element in a geometric algebra.
Or differentiating a product of two functions is a derivation, of course, on function.
Yeah, but I'm just saying that we can think of derivations as vectors in a vector space, and that vector space can be a subspace of some geometric algebra.
Yes. Mm-hmm.
Right. So it can be
that, for example, is more general, of course.
Yeah, but I'm not worried about that. Just abstractly speaking, that there are, if we consider only the degree 1 elements of a geometric algebra, they form a vector space.
Okay.
right?
But of course, the
Um,
whole Clifford algebra forms a vector space too, if you want to look at it that way.
Over, yes, but but what I'm want to ask is, if we have a degree one element that is corresponding to a derivation, what kind of element corresponds to a co-derivation? So we need to be able to operate by that element alpha. Suppose alpha is an element in some geometric space or geometric algebra, and x is a degree one element in the geometric algebra. Then what element in the geometric algebra can we use to represent alpha? And so we can't, if we just multiply, if we use Clifford multiplication and we multiply alpha by x, like maybe it's a, say it's a four-dimensional geometric algebra, then maybe this is something like a what? I don't know. Like the inverse of x, for example. Right?
Yeah, see, when were covectors invented to begin with? It goes back to what, the 19th century or
Yeah,
earlier?
Ricky.
Was that invention of tensor algebra when covectors? What is the history of covectors?
Yes, it is. It's definitely part of
Tensor analysis.
Tensor analysis, right? Tensor.
So that was the 19th, well, the 18th, 20th, 19th century, I guess the ideas arose. Well, of course, that's when matrices, the idea of matrix multiplication was what, Cayley's invention, which is very interesting, of course.
But this notion of derivation as derivations over an algebra as forming a vector field is quite new. It's early 20th century.
Well, yeah, that's
I mean,
differential forms. I guess you can identify that with differential forms.
No, it's part of abstract algebra and the whole notion that in abstract algebra we can abstractly define the notion of a derivation.
Yeah, that's right. Yeah.
The fact that derivations formed vector spaces, or actually more like a vector, that derivations corresponded to vector fields, that's
Yeah, tangent spaces and so on.
But I always thought it was interesting that Zbigniew was, he was well versed in sort of modern differential geometry that talked about tangent bundles and so forth, but he abandoned all of that geometry. Like he basically said, fundamentally, I'm not really interested in geometry. I'm interested in the algebra that underlies this geometry. And he started basically with Grassmann algebra.
Okay, yeah, I agree. I like that because, like I say, I think any matrix can be represented as the Grassmann algebra and its co-Grassmann algebra. So
Yeah,
compatible, what I call compatible Grassmann algebras. Simple, and the 2x2 case is just AB plus BA is equal to 1, where A and B are nilpotents. I think that's very basic to the whole structure of any matrix. You can relate it back to 2x2 matrices and construct higher dimensional matrices by the Kronecker product of these lower dimensional 2x2 matrix algebras. So that's all of Clifford algebra as well, really. So a
But
matrix,
normally we're thinking of matrix algebra as representation, like so some quotient. So we're thinking of this matrix algebras as sort of being arrays of scalar values that are defined once you define a basis in some space, right? And so then the matrix algebra matrices represent linear operators in that space.
or you can say they represent Clifford numbers.
Yeah, but you're doing something a little different. In fact, you're sort of going the opposite direction. You're saying we have this abstract thing called matrix algebra, and then you're saying, how do we represent that as a pair of compatible Grassmann algebras?
Yeah, well, it's yeah. Yeah, I think about it, a matrix is just the coordinates of a geometric number. Any matrix can be thought about as being the coordinates of a geometric number. In fact, there's many isomorphisms that are going on there. But the interesting thing in physics is that, for example, the relationship between the Dirac algebra and the Pauli algebra. And you can consider the Pauli algebra to be the Pauli algebra of an observer as the even subalgebra of the Dirac algebra. I think that's very important. That's not a viewpoint that everybody, all physicists share yet at this point. But that, I think that was Hesnes' genius. And all this Clifford algebra stuff is really taking off on using matrices. Well, the Pauli algebra is the even subalgebra of the Minkowski-Dirac algebra of space-time.
That part of it somehow looks like this this algebra map, right? It's mapping between two different Clifford algebras, two different geometric algebras.
Yeah, so Zbyszek only used your pi mapping and your and the other one, that's just two nilpotents that sum to the identity element. He only used two. He used
two idempotents.
Yeah, two idempotents which sum to the identity. He only used two. He never, a matrix, for example, you take ones down the diagonal and you have many idempotents that sum to one. 1, 0, 0, 0, 0, 1, 0, 0. You know, in an n-dimensional square matrix, you have n idempotents that sum to the identity matrix.
Mm-hmm. But now you're talking about matrix algebra, right? You're not talking about geometric algebra anymore.
Well, that's all right. So you can think about your vectors and covectors define where you equal that to the identity as a 2x2 matrix, with one representing the pi operator and the other one representing the other one on the diagonal of the matrix.
Yeah, well, but you pointed out, right, that we can take a matrix and represent it as a pair of compatible Grassmann algebras, as the name.
Well, of course, we could take an n-dimensional matrix and divide ones down the diagonal, and then the other half with zeros, and then the other half with ones down the opposite diagonal, and they sum to 1, 2. Then, so then there's many matrix algebras that you can define two idempotents equal to the identity matrix, where in this case it's an n-dimensional square matrix and just divided in two parts. Or, for example, matrix representation of the quaternion algebra.
Okay.
So thank you.
Okay. Yes, I'm sorry. I should be watching the clock.
Yeah. Okay.
Yeah, people, they're gesturing. I have to go. Okay. Thank you. I apologize.
No, thank you for participating. Yes, I realize that we've sort of gone past time, so I need someone to be tapping on my shoulder to say it's time to stop. But let's just decide maybe what to do next.
Okay.
Yeah.
I think that it can be interesting if Professor Sopcich can present to us how he made the split of one matrix from the spectral analysis theorem. I remember that you say that using the spectral theorem, you can write any matrix in terms of idempotence and nilpotence.
Yeah,
Then-
I like to say more. I've been thinking about that this week, actually. And I in another couple of weeks, I can give a talk about that if you like.
Oh,
With only the 2x2 matrix and the 4x4 matrix. After that, it's all the same. So if you understand the 2x2 case and the 4x4, how that arises and what Clifford algebras are associated with it, you really understand everything then, I think.
okay.
So
Yeah.
I am working on that right now, trying to make it in the most clear way I can.
Because I think that it is related with the question that Professor Pesch was presenting just now. Then I think that this can be important to
Yeah, well, it
understand.
would be nice to get the idea of this three observer, what the your what is that group? It's not a group, but what's the other
Groupoid?
group? Yeah, groupoid.
Well, yeah, but that's a somewhat different question still. I think I would put that in a different category, but of interest. But what Jesus just mentioned was that you have this result that you showed us 2 weeks ago that showed that we could take any matrix, so let's say any linear operator, and then using the construction that you showed, we can split it into something in two Grassmann algebras. Well, that form
Yeah,
together.
I can do that very nicely now, but I can talk about that.
So in other words, we just very abstractly, we can take a linear operator and split it into something that is composed of nilpotents from one Grassmann algebra and nilpotents from another Grassmann algebra.
Exactly.
As merged into some kind of geometric algebra, right? So,
Exactly.
so in other words, we can map a matrix directly into an element of a geometric algebra. But
That's
this element of the geometric algebra has a structure, has a specific structure that can be described in terms of two compatible Grassmann algebras.
Exactly.
now-
And that satisfies that simple identity.
So the question that I think that Jesus is raising is that, is this kind of split that you're talking about, this split representation of a linear operator, is that somehow related to the split that was presented by Oshevich, right? And this, the pi and d as being.
Yeah, I think it must be. It has to be.
Well, the problem I have with the presumption that that's true is that it looks to me that like the two algebras, the two Grassmann algebras involved are sort of too similar to each other, right? Because when we operate with pi on the Grassmann algebra, we get another Grassmann algebra. But if we operate with D on that same Grassmann algebra, the result isn't a Grassmann algebra. So it's kind of like the same. My point of view would be something like, if we view the Pauli algebra as the even subalgebra of the Dirac algebra, what's the complement, right? Like what's, so if we take out the even subalgebra, is there still an algebra left over?
Okay.
You know, like it's, and if we don't have a way to represent what the part that's left over, then I don't see how we can set up the duality that Ushevich is after here. Right?
Okay, well, I think we can do that. I don't think it'll be that hard, actually. That there's, well, there are different kinds of operators involved, which is what needs to be clarified.
How do you connect operators and multiplication in an algebra? Like that, I don't know. I mean,
Well, the good example is the Pauli algebra or the Dirac algebra.
but we can do it as you said, when you resort to the representation, then we represent the algebra in a certain, you know, as a set of linear operators. That sort of makes sense to me, but
really everything is a representation. Even language is a representation of what the ideas that we're talking about. So anything you're talking about is a representation, really. Not just vectors and covectors, but language itself is a representation of ideas that we're thinking about. So,
okay.
Yes, but the idea of a representation of one matrix in terms of their own structure is really exciting, because I think that we then, for that matrix, we don't need another kind of representation, because in the same matrix we have the necessary for that in any kind of reference system we can present in this way. But maybe this is a question of for the next 2 weeks.
Yes. So can we, when we meet again in 2 weeks, Dr. Sobczak,
yes, I think that's
You-
fine. Yeah, I'll be.
you can present something along this line again, or
Yes, I
maybe even,
can. Yeah, I may actually be moving back to the United States for a little while. So at the end of this month, so I'll be back in South Carolina then. But yeah, 2 weeks would be a good length of time for me to get back to the States.
so in 2 weeks, will you be back in the
Yes.
US?
Yeah, we're leaving actually on the 29th. So in 2 weeks, that'll be about 8 days from, and then in 1 week, we're leaving for the States. So another week, we'll be back.
I hope the transition is easier for you this time.
Well, that's the thing with this COVID, you never know what's going to happen. Flights can be canceled, all kinds of problems.
Well, good luck.
Thanks.
Okay, well, thank you very much. And I'll see everyone again in 2 weeks.
Okay.
Okay, that's perfect. It was a very interesting talk that you gave today.
Yeah.
I
I wish
think
it
this idea,
wasn't.
yeah, that's it. We can talk further about that too, of course.
Yes, I'd like to sort of focus on this for a little while, and then in the future, perhaps go to this issue that you bring up quite often about relative velocity as being binary or ternary. And
Okay,
that's
sounds
an
good.
interesting subject, but a separate one. So focus on
Okay.
this for a little while.
Okay,
Bye for now.
okay. Take care.